Hydrologic Research Center. We are located in San Diego, California. The center was established in '93. It's a non-for-profit research, technology transfer, and training organization. Our objectives are to help bridge gaps between scientific research in hydrology and application for solutions of important societal problems that involve water. So this is a big task, but we will do our best. Next. So I'm going to present two case studies that were studied for a long time in our center, and they are very different type of extreme events. So the first one is extreme events with extreme impact. This will be through a presentation of a case study that was done for the Panama Canal Authority, analysis of the very extreme, the event that was not observed yet, that they would like to, at the time they wanted to use it for the design of the new set of canals. And they wanted to see the impact of the very extreme of this event. And I think through the story you will see some of the issues in the scientific approach of risk assessment, and hopefully I'll be able to demonstrate them. The other one is the non-extreme events with extreme impacts. And I'm going to talk about flash floods, which these are events that might be the 2-year return period events that still have extreme impact. And how do you assess those changes in the face of climate change? So I'll start with the first one. This is a study that started in 2007, maybe even earlier, and we were asked by the Canal Authority to come up with the biggest event that we can come up with that is probable, and to run this event through a series of models that simulates the rainfall, the stream flow into the lakes of the canal watersheds, and do also an economic impact analysis and assessment of the impact of such an event. So this is the country of Panama, and this is the canal watershed, the Panama Canal watershed. This is a zoom into the Panama Canal watershed. This is the canal. The canal has this Lake Gatun, so the canal goes from the Pacific to Atlantic, and it basically has this series of locks. I'm not going to explain it. Probably most of you knows what's going on, but this is a big features of the canal, the Lake Gatun, and this is the main water resource for the canal operation. This is Lake Madden that drains the Rio Chagres, the Pekini, and the Bucaron watersheds. And this water is being used to raise the level of the canal and to operate the locks, and to and then being released, most of it, into the ocean. So when you ask someone to estimate the events that was not occurred, the common practice would be to take observations. These are observations on the x-axis. I'm describing a return period and the depth of precipitation for different duration. Here we're talking about 1 day. And you fit extreme value distribution, in this case the generalized extreme value distribution. So you assume that the extreme values of the major events, they follow a distribution, and you can look at you can fit different distributions, and you can look at the tail of the distribution. So that would be the engineering approach. On top of that, we augmented the observed record. We said, okay, we have only, and this is Panama Canal, we have very good records. Records started from the early 1900s, and many gauges in the 3,000 square kilometers of the canal watershed. So this is a kind of a a record that cannot be found very easily in other places. This is a very detailed observed record. So we also augmented the observed record by looking at paleoclimatic flood events, if there are evidences of big floods that can be maybe detected by paleoclimatic studies. We built a stochastic model looking at the statistics of features of the existing records and saying, well, these type of events have not occurred, but there is no reason why, from statistical point of view, they could have not been part of the record. So we had a stochastic weather generator that simulates likely to occur events, looking at the features of the observations. And then we built also an atmospheric model, and we moved through the model scenarios, events that occurred in neighboring watersheds but were not seen in the Panama Canal. We also looked at the impact of hurricanes. We talked a lot here about hurricane tropical storms, but in Panama Canal, in the Panama, actually, that's the southern tip of the hurricane zone, so you don't get many hurricanes. In fact, historically they got only one or two, but we simulated hurricane moving through the watershed. In fact, it's not a damaging storm because the country is so narrow, so by the time it moves through the country, you don't have lots of rainfall dumped into in the watershed. So, and then we tried also modifying the atmospheric model with climate change scenarios of increasing temperature and increasing capacity of moisture holding in the atmosphere. So all this was done, and I want to talk a little bit about what is it when you look at the rare events like that. You have to put some kind of a threshold, and this is fairly arbitrary threshold. So basically, you talk about events that has not been yet observed. You can talk about rare but probable, but at a certain point, you can say you should say that there are events that are unforeseen. That you have to say, well, beyond this point, I think that this is not reasonable. If you look at the return period curve and return level, which is basically the probability of a given return period occur, so it's a probability of an event being exceeded in a given year, and this is in percent, and this is the return period. So we all know that the 100-year return period is a 1% return level. But below that, when you talk about the 1,000, you talk about 0.1%, and when you talk about the 10,000, you talk about 0.01%, and your observation basically describe this area. And if you assume that as you go to less probable events, the event will be bigger, then there is really, you're talking about very, very small probabilities, and at a certain point you have to say, well, there is a place in which I think this will be foreseen. It hasn't occurred, but maybe will occur. And this is, we cannot deal with that. We have to put this threshold someplace. Because really, in the daily life, how would you plan for an event that is 0.1% or 0.01%? They are both almost zero. So there's a point in which you put this threshold. So for this study, just for the sake of argument, we'll talk about 1,000-year return period that is being unforeseen. That's for so we did this study, and that was lots of work since early 2006. We had a few reports, and final reports in October 20th, October 2010. Many weekends and nights, and we put the likely extremes through a series of models to simulate the flow and to simulate the lake level in Gatun. And we have a model that actually can optimize different management schemes of the lake through the canal. And then there was an economic analysis of the expected damage from the very large extremes. So this was all submitted in October 20th, 2010. And why this is important? Because in December 2010, between 6th and the 12th, there was a very large event on the canal. There was the low pressure that was fed by the ITCZ, and it was a persistent storm that lasted for 6 days and didn't move anywhere and dumped lots of rain on the eastern part of the canal. And that's some of this event caused fatalities. It was the first time that the canal was experienced a closure from a natural disaster. There were closures before, but natural disaster, that was the only event since early on, and lots of damage. The whole water, the potable drinking water infrastructure failed. There was no spill from the Gatun dam, but it was almost, the lake level was very high. This is a picture from the Lake Madden and the full capacity of the releases under the Gamboa Bridge, which is the dam that releases water downstream. So this event, if you look at rainfall average over the canal, over 3,300 square kilometers. These are the annual maxima, so that's the largest event, 24 hours event that occurred since 1940 to 2010, 2009 I guess, that's the last one. This event that occurred between December 7 and 8 measured 276 millimeter over the entire canal in 24 hours, and it was twice as large as the previously largest event observed. So this is 2 months after, month and a half after we did our analysis. In fact, if you look at the biggest event, and you are not associate them with year, just the ones that over some kind of a threshold, there are 3 big events that occurred in November, December of 2010. The third largest event occurred in November 7, and there was actually another large event that can be part of the family of large events that occurred in December 25, 26, and this is our event in December 7 and 8. So this is a work that was done completed in 2007, in which we tested all these methodologies to see if what would be the large event, and now we have a reference, the 276 millimeter that occurred in December 2010. The maximum previously observed record for this period of the study from 1908 to 2007 was 124 millimeters over the entire canal. The maximum stochastic weather generator that we were able to develop was 315. This is the maximum, so the very low probability. We generated many realizations from these weather generators, and only few got into this scale of the event that we had, 276. If you use the empirical method to estimate the maximum probable precipitation event that can occur, and there are different methods, we actually got a very small value, less than the event, half of the event, less than half of the event that was observed. And in the atmospheric model, out of 20 simulations of what if, of weather moving and climate change, we got only one simulation that were able to simulate a little bit more than not a little bit, more than the December 2010 event. So we raised the questions, was this event, before it happened, was it probable? Was it reasonable to estimate that event like that will occur? And here I'm showing a return period, a simple return period plot. This is the return period, 10, 100, 1,000, and beyond 1,000 we call it unforeseen event. This is millimeters, so we have the December 2010 event and all the series of large events that were annual maxima of large events that occurred before that. And if we fit a distribution, the GEV distribution, we get, if you look at the optimal line that you get, and the cross between the event, the 2010 event, and this is beyond the 1,000-year events. So this is unforeseen event for the sake of argument. But if you look at if you start looking at the uncertainty, at the confidence bound of this estimate, you can see that in the 95 percentiles, this event is about 140 years. So definitely an event that could have been foreseen. So if you think about that, if you look at as you start predicting on the tail, on the events that were not foreseen, the uncertainty bound are increasing as you go to lower frequencies of events. And we kind of, you have to look, this is a cross-sections of the 200-year event. So it's basically looking at the distribution of values of 24 hours rainfall simulation of these cross-sections. And you can see that the December 2010 in the 200 years event had about 15% of the times this event was predicted or exceeded. So you have to look at that, and maybe when you present things like that, you have to present the upper tail, the ones that you are more conservative. Because if you present the optimal here, you can see that actually because of the exponent on these lines, as you go further, the differences are getting bigger, and the confidence interval of the upper tail, of the upper confidence bound is going further away. So it's not even the median. So if you report the optimal event, it's less than 40% of the time not covering it. 60% of the times you are underestimating your optimal. So it's very important to include the uncertainty in the risk assessment of that, and the uncertainty is very large. And I guess that's talking about what we heard this morning about how to do risk assessment. So I think in risk assessment you have to realize that there are things that you don't know, and you have to know what you don't know. So this study was revised, and we revised basically the stochastic generator to include this extreme event and to be able to simulate that. And after the revision, the return period of this event came to be on the 95 percentiles bound about 30 years return period, and on the optimal lines about 150 years return period. So definitely now that we experience these events, the whole return period graph looks very different. And then we got all these events through the set of models, and here I'm showing just the Lake Gatun level, and we were able to get a risk assessment of the return period. The return period here is now on the X, Y, and the lake level, and we know that this level, 90.5 feet and above, cause a closure of the canal, and above 92 feet, you get failure of the canal, and you can actually estimate the economic losses due to these two thresholds. So now I'm going to shift gear into different type of events. These are flash floods events. I'm going to talk about California. And I'm going to talk about Southern California, which is from Santa Barbara, a bit north of Los Angeles, all the way to San Diego. So this is a zoom of this area. In this area, we have two mountain ranges that can be described as the transverse range and the peninsular range. This is a work that was done by my colleague, Dr. Modric. That was her PhD dissertation. And she actually looked at about 1,000 small basins along these mountain ranges in a very high resolution, about 26 kilometers. And she tried to assess what would be the impact of climate change on these small, relatively small events. And why these are important? These are based on WMO report from 2008, and there were other reports like that. Out of 139 countries, 105 indicated that flash floods were among the top 2 most important hazards around the world and require special attention. So this is a number of natural disaster types, and you can see that floods, and most of it is flash floods, is the major cause of fatalities and damage. It's not making the headlines, but if you count them all together, these are very important natural disaster. But this doesn't have to be from a tropical storm or a hurricane or a big storm. This can be the 2-year, 3-year return periods, maybe 5 years, depends on location. So these are not extreme events, but with extreme impact. In Southern California, when you look, so Dr. Modric built a set of models in which she can force precipitation into a hydrologic model and get estimates of flow and some kind of estimates of flash flood occurrence. In Southern California, when you look at sea surface temperature relationship to rainfall, you see a very strong signal between La Nina years and El Nino years in the precipitation. But this signal is magnified when you look at stream flow. This is the same graph, the same events for stream flow. So it's very important in Southern California or in this study, to capture the detailed hydrology to cause these differences to magnify. And this is mainly the feature of the rainfall and the feature of the land, and how this is being translated to this. So in her study, she has a climate model, CCSM at the time. That was it was completed already 3 years ago, and she did it, I guess it's 5 years ago, so it's not the most updated. But just to get the idea, the CCSM was forced to 2 periods, 20th centuries and 21st centuries. She had dynamics, a downscale model or graphic model to take the large scale and to create high resolution rainfall input into the model, and then hydrologic and geomorphologic models to see how the frequency of flash flood occurrence. When you look at the output of the dynamic downscale models, and you look at the climatologies of the 20th centuries and the 21st centuries, nothing jumped up. In fact, the statistics of this and this doesn't tell an interesting story. There is no differences in the projected future. But when you look at the frequency of flash floods occurrence, the 20th centuries versus the 21st centuries, you can clearly see that there is an increased frequency of flash flood occurrences in the 21st centuries, and the red and the blue represents 2 different hydrologic models. And these changes are due to changes in rainfall magnitude. The short-term rainfall magnitude increase in the event distribution, so you get, after the downscaling, you get less event, but more, but stronger. and decrease in number of events. So I guess I said that. So it's the features of the rainfall distribution, the temporal rainfall distribution, that creates these differences between the observed record and the projected record. So the two take-home messages is the prediction of extreme events with extreme impact must consider the uncertainty bounds. And we know very little about what happened, what didn't happen yet. So we have to consider the uncertainty bounds. The climate change impact on frequency of flash flood occurrence has to consider properties that dominate the local hydrologic processes. So it's not enough to look at the output of the climate model. You have to put it in a hydrologic model that knows to describe the local features of the research.